Guys, you are welcome to the continuation of our tutorial on deep learning. Now, the last time we talked about the linear regression with one variable. We said we want to actually draw a line that will fit into a data point. Now, the equation of this straight line in red is y equals to wx. So what our machine learning model is trying to actually learn is this equation that will actually be the best equation that will fit into our data point. So now this is a typical example where we have a house prediction problem. In this case, we are predicting the price of the house, and as you can guess right that this is a linear regression problem because the price of a house could be an infinite in an infinite range of numbers. So we're predicting a continuous number. So now we have an existing data point of the house prices, and the feature that we're given is size. Now, when we plot our existing data point, or what you can also refer to as historical data point, on a plot chart, you see that it looks this way. So each of these x represent the data point. For instance, if you look at this, it means that if the size is close to like 1,000 square feet, the price is around close to like $200,000. So this maybe around 170 $180,000. So likewise the other one. Now we are now building a machine learning model such that if you have a new data point, something here, our model should be able to tell us what will be the prediction for that particular point, what will be the best price prediction for that. So now we try to learn a model and draw a line. For instance, if we decide to pick this line in blue as our model prediction, so it means that when we have a new point, say for instance, if you have a new point in this place, then this line is going to predict that particular price for that particular point. Is going to have this equivalent of 1250 square feet and 220 price, $220,000 in price. But you can imagine is I decide to draw another line this way, you will see that it will have different feet, or I draw another line this way, or I draw a line this way. So each of these lines are different guesses, different models that possibly you could have, but each of these lines has different performance based on the plotted data set. So now this is the data representation. This is our feature in square feet. So in this case, we have just one variable, one determining variable. So this is our independent variable, and that is the square feet. Now price is our y, which is our dependent variable. That is, the price depends on what the square feet is. It varies with the square feet. So, and this is the way we represent it. It's also referred to as target variable. Now this representation shows each instance of the training example. So how do you build a model? How to bring a model is, remember in machine learning we're trying to learn from data. So we have a training set which we have plotted. We saying that we feed in our training set into a learning algorithm, and with this we learn an hypothesis that we believe should best give us the best approximation to the exact function. So this is a typical machine learning pipeline or workflow. So Then we build in, after we have learned our hypothesis based on the training set and the learning algorithm, then we can now feed in a new size of a house, which is our independent variable x. Then we get an estimated price based on that, which normally you refer to as y hat. Now, so how do we represent h? H is what we want to learn. So how do we represent h? Now, we can represent our h with this equation, which is w0 plus w1x. Now, what does this equation represent? If you go to linear algebra, you can recall, you will see that this equation mimics what you call this slope of a slope of a straight line. So in this case, we have this w0 as the intercept, and you have this input variable, and you have w1 to it. Okay. So I think that is the w1's gradient, if I can remember correctly. So estimating HW of x that minimizes a cost function. I did a tutorial on cost function, objective function, and loss function, which you may want to look at to have an understanding of that. But essentially, cost function is referring to how close are we to the exact prediction, or how far away is our prediction, that is our y hat, how far away is it from our y. So we're learning h, which is parameterized with w, and we are having input to our function as x. So our function takes in x, which is the independent variable, and needs to learn and the w that makes our y hat to be equals to y. Don't forget that we mentioned that w are just a bunch of numbers with matrices, and just numbers matrices. So how do we choose our w's? So that is exact thing that I just mentioned. We want to learn the w's such that we'll be able to have the best possible hypothesis for this training set. So the model parameters are essentially w, which also referred to as weight. In other literature, you may see them represented as theta. So there are various ways for which we can build an hypothesis. As you know, the hypothesis is an assumption trying to learn some approximate the exact. So if we decide that this is the equation for our hypothesis, and we randomly choose some values of w0 and w1, if we decide to choose w0 to be equals to 1.5, and we choose w1 to be 0, you know that if we choose w1 to be equals to 0, that means that what we're essentially saying, irrespective of the value of x, the hypothesis that we are learning will just be constant. That means our hypothesis is it doesn't change. It doesn't is not affected by the value of x, because we chose w1 to be equals to 0. And you can see it in this place. Irrespective of where the data point are, our line of equation just remains constant. But if we choose w0 to be 0 and w1 to be 0.5, which means that it's like half of whatever is the value of our x. And in this case, we are trying to change the intercept. What is the difference between this and this? Now, it's possible that because our w0 is 0, so it's starting here. So if all our data clumps around this area, then we can be sure that our intercept is going to get a line through them. Our line of equation is going to move through the data point because of the choice of our intercept at 0. But if our intercept is somewhere here, and our data point is somewhere here, and we are now choosing our intercept to be 0, you can see that we have already missed all the data points. So by varying the intercept in this place to be 1, this will be a better suit. This will be a better suit for this data point. Alright. So how do we choose our hypothesis? The idea is we choose W and W naught such that the hypothesis is close to y hat for our training example, and that's what I said. This our h w x of I is refers to our y hat, that is our predicted. Whenever you see the hat on the y, it's showing our prediction, so our predicted y. So we want it to be as close as to the actual value of in our training example. But we're not just doing it for one particular training example. We are looking at each of the instances in our training example and make sure that the total loss between our y hat and y for each instance of the training example is minimal as much as possible. So we look at our error. The error will be the absolute difference between the predicted value and the actual value for each of the training instance, and we sum up all of them and we try to do some normalization by dividing by 1 over 2n of the total 1 over 2n of the total loss. In this case, the n is the total number of our training examples, which if for instance you have maybe here you have like maybe 100 or 1 or 10,000 training examples, so our capital N is going to be 10,000. Now, to be able to have some mathematical ease, so we square it, which is like trying to do a mean square error. So this is mean square error calculation. So you may want to look at that. There are different kinds of error metrics. So you have the mean square error. So and that is what is being calculated. The best fitting line is defined by W, which is a bunch of numbers that minimizes the total error, which is E. So essentially, as you will see in machine learning, the error is very important. We're trying to actually define a loss function we define our error equation for any particular shades of machine learning or deep learning problem. So forming a particular error is quite important. Being able to have a good equation to for measuring the error in whatever problem is of concern to us. So the cost function, we're trying to minimize W0 and W1 such that the difference between the actual and the predicted is as much as possible close to 0. We want the difference to be as much as possible close to 0. It's not possible for us to get exact 0, but we want something that is as close to 0. If we are able to get the predicted from values to be exactly 0, that means we're having an exact function that actually represents our data point. Alright, so we choose this as we have mentioned before. So our W0 and W1 are the parameters that we have in our data. So here, these are the different hypotheses. Based on the choice of our W0 and W1, we see that our line of fit moves differently. Here W0 is 0, which means that the line is going to start from 0. Here W0 is 1, which means that the line is going to start from 1. But essentially, we're trying to minimize both W0 and W1. In a case when we have chosen our W0 to be equal to 0, it means that we have already reduced number of parameters to just one, W1. So here in this case we're just minimizing only W1, as you can see here, because W0 is no longer taken into consideration. It is fixed to 0. So for the fixed one, where we just have a single parameter of say W1, so we can see in this case, if we choose W1 to be equals to 1 and you feed into the equation, you see that we get 0, which you can actually see. Now this is our simple example here. This is our data point. These are x and y values. The red shows our training examples. So when x is equals to 1, y is 1. When x is 2, y is 2. When x is 3, y is 3. And so we are now drawing a line. So our hypothesis is this black line that we have drawn through the data point. and because our line, our hypothesis line, is able to pass through all our data points, we're able to get is 0 error. By the time you do this calculation, you discover that the difference between our actual predicted and the actual values is 0 for each of the data instance. Then our total error gives us 0. uh, Now, and this is how it is actually measured. We are trying to measure the difference between predicted, which is this line of equation, and the actual. Now what this is saying is that if we draw another line here, we chose our W1 to be 1, which is the perfect fit, but if we chose our W1 to be 0.5, you see that we have an error. This is 0.58, which is greater than 0. So this one is better than this hypothesis is better than this hypothesis on our training examples. So you see how this is measured. We take each instance of our data point, the y of our data point here. Y is 1 and 2 and 3. So these are 1, 2, 3. Then we trace the prediction for that. So it is predicted 0.5. So when it's actually 1, then our prediction is 0.5. Here, when y is actually 2, our prediction is 1. Here, when y is actually 3, our prediction is 1.5, like you can see here, and we measure the error. So you can see that as we continue to vary our best line of action based on our parameters, we begin to get different lines, and you see the error here is actually greater than what we have here, 0.58. Now the error has increased, and what we want a line that will give us as the best minimum error as possible. So now you also see here as well that as we have different errors based on our error analysis, you see that our total error when W1 is equal to 0 is 2.3. So if we plot a graph of W1 against our total error, so when W1 is equals to 0, we get our error to be 2.3. So we plot that here. When W1 is equal to 0.5, we plot our error to be 0.58. So that is this point. When W1 is equal to 1, we plot our error, our total error, which is 0. So W1 is 1, our error is 0. So by the time we do all these plots, we can see this gives us what? A bow, or what you call a bow. So this gives us a bow, and that is the plotting our total error, which is parameterized with W1 against W1, and we see a bow. Now what this is actually telling us that the best line of the best equation is actually the one that gives us the like the base, that is what you call the global minimum. So yeah, where you have this global minimum, that is where we have the best particular parameters, the best parameters for this problem. So how do we minimize this total error so that we'll be able to get this particular point, get to this particular point that gives us the optimum, what you call the global minimum here? So what do we do? That gives us takes us to having to do what you call optimizer, how we have to optimize our W1 and W0 to be able to go down the steps. So, and that takes us to gradient descent, which we will see shortly. So this is just a summary of what we have seen earlier. We are trying to minimize our total error. So now this is when we now have two parameters. In the earlier ones, we have fixed W0 to be equals to 0, but now we're now saying that W0 is also changing, it's not just 0. So we now have two parameters now. So when we have two parameters, by the time we do the same thing that we did here for just one parameters, because this can just be plotted on the 2D but on x and y axis. But by the time we now have more than one parameters, like as in this case where we now have two parameters, w0 and w1, we see that the plotting of our graph with w0 and w0 and w1 with it plotting with our total error gives us this shape, okay, which is like a bow as well. So and this is an ellipsis, when just for us to be able to visualize how our error, we're trying to visualize our error against the parameters, the total errors against the parameters. Now in this case you have our w0 and w1. These are training examples in x, and this is our current hypothesis. So and when we're trying to plot w0 against w1 based on our choice, you can see here when we choose w0 to be 800 and we choose w1 to be minus 0.5, you can see the points that we have. As we change observe that this line is changing. As we change this line, you see again the next one, choice of our line. As we're changing the line, observe that this is also changing. So this is actually our interest. This is where we want to go. So as we're changing this line, this point keeps moving towards the direction of what you call the global minimum. So you see this line changing, and you see now you are now in the position of global minimum. So how do we move? How do we get to move from wherever we have to this center? Because this is the center that gives us the best parameters, the best values for w0 and w1. To be able to do that, we need what I mentioned earlier. We need to do what we call gradient descent. And gradient descent allows us to minimize our cost function. So remember, the cost function is something as loss function or the objective function. So we want to minimize w0, w1. So we start with some random values of w0 and w1. Basically, we start with non-zeros. Then we keep changing the w0 and w1 to reduce our total error until hopefully we end up at the global minimum. So here we can start from just anywhere. So this is, remember, our objective, our goal is to take steps until we get into a global minimum. So we want to land in this place, seems like the global minimum. So we want to land in the best possible global minimum. So let's say we choose w0 and w1 such that first of all we started randomly from anywhere. Maybe we started from this place, and so we continue to take steps one after the other until we actually hopefully move in the direction of the global minimum. But you can have different local minimum. This is another place, this is another place that we can end up in. So this is another place, like I said earlier, that we can end up in. So how do we take these steps such that we move in the direction of our local minimum of the global minimum? So for us to be able to do that, we use the technique called the gradient descent. Essentially, what gradient descent is doing is, the gradient descent equation is this, and what it is trying to do is, you are going to take a differential equation. We're trying to use calculus here. You take a differential equation to be able to learn the direction to which to take the steps. So here in this case, you have wj is equal to wj minus alpha, and alpha here is the learning rate. The learning rate is telling us how much steps we should take, how much baby steps we should take to be able to move in that direction. Then we do a partial derivative for each of the parameters that we have in our total error, so to be able to learn in what direction to move. So, and the correct way of doing this this gradient descent, which we do multiple times until we don't see a change in our values again, is we first of all take the first parameters and we compute and this value we store in a temporary variable by taking our w naught, take a partial derivative of the total error and multiply by our learning rate, and we store it in a temporary place. Then we also do the same for our w1, we store it in a temporary place. Then we put the value of w naught, we replace the value of w naught with the temporary first, the temp 0, we replace the value of w1 with temp 1. This is an incorrect way of doing, so this is how it is done after you have calculated for each of the parameters. And as you can imagine, we can have more than more than two parameters. Here we have w0 and w1. We can have up to like maybe 30 w's that we need to learn. So we do all of this before we now begin to update the values inside. So if our alpha is too small, our gradient descent can be slow. It might take us forever before we can actually get to our local minimum. And if it is too large, we can actually overshoot our minimum, or we can even diverge, and it will give us maybe not a number or infinite. If you have actually done some of this, maybe write a Python program, if you see not a number or infinite, that means that your gradient descent has actually diverged. And so and what you need to do is to reduce your learning rate so that you can take baby steps towards the local minimum. So this is for linear regression, the gradient descent algorithm for linear regression. And how is this going to be applicable here? Now this is our hypothesis. So remember, this is our hypothesis, and this is our error. So here we can substitute our this refers to the model that we are trying to learn for that's the model we're trying to learn for a linear regression. So we can substitute this inside this particular equation to be able to measure our total error. So if you do that, you discover that when we're trying to calculate our gradient descent and we do a partial derivative, we substitute this one with this. Now you need to recall, be aware that we are substituting this in this place, HWXI, we are substituting this for this because this equation is actually for linear regression. As we go into other models, this equation will be different. So we do this math. As you can see here, we have trying to take our j when our j is 0, that is taken for w0, and we do our differential, do a partial derivative. We have this when our j is equals to 1. If you do a partial derivative, you have this, and you can do that as an exercise. You discover that that's what you're going to have, because this is essentially what we're trying to do. We're trying to do a partial derivative for each of the parameters, and our e is equals to the whole of this. So we're doing a partial derivative here. So if we substitute our j to be 0 here, we get this. This is what we get. And if we substitute our j to be equals to 1, then we're going to get this as our final result. So these are our two final results that we have. So gradient descent for linear regression, we do this, we update w0 and w1 simultaneously until it actually converges, because now we have learned what the values of our w0 and the values of our w1 is going to be in for linear regression. So now there's a concept of batch versus stochastic gradient descent, and what this is saying is, let's say we have 10,000 training examples in our examples. Are you going to now pick one example after the others and start doing gradient descent on that? That is, you start picking one example, calculate the error, do gradient descent, pick the second example, calculate the error, do gradient descent. That is not That's not the best approach to go about it. So what you actually do is that you can decide to do each step of the gradient descent uses all the training example. You can decide to calculate all the training the errors at once. Then you now do gradient descent. That is, before you take a step, you first of all get to find out the values of the total error using each of the training examples. Or you can take use just a subset. Maybe out of this 10,000 you can begin to update after 32. You have actually passed 32 training examples through your model, and you decide to update and take a step towards the minimum. Or you can just arbitrarily use one training example out of so many to be able to take your step, and this has proven to work very well. That's what we mean as stochastic, that is randomly taking training example and taking step based on that. So this is for univariant linear regression, and it's univariant because you just have x. So you just have x1, that is one feature, just one variable. Now if you are now modeling a linear regression using a neural network, this is how you go about it. This is also referred to as linear perceptron. Essentially, what do? You have your bias, which you can be fixed as maybe 1, and you have your input x. You remember that each of these node represent what you call our neuron, and our neuron is a symbol for computational graph. They're actually holding our values or doing a computation. So here we have x1 for our input, and each of the arrows, this directed graph, each of the arrows goes to the next layer. So here we have the output layer, which is just one neuron, which is supposed to hold the data for our predicted values. So what do we do here? Here in this case, we are computing the summation of our W0 with W1 multiplied by X1, and that will give us our output. So this is the implementation uh, of this previous graph using uh, um, TensorFlow. So if you want to model this graph using a TensorFlow, so this is the code for doing that. You have a function that takes in a new input that you want to predict, and what that function is, we have already coded our training examples and with their corresponding predictions. So this is the predictions, this is the prediction, this is the input, this is the prediction. And so you just in TensorFlow call tf.keras. Remember, now we have imported TensorFlow as tf. So you are using keras on top of or TensorFlow on top of keras, so integrated together to be able to build sequential. This sequential is just saying you are trying to learn a linear function. So this is just a sequential layer in keras, and you are having here you are having calling the dense layer. This dense layer means linear, and sequential means you want to maybe like stack to stack a layers of neural networks. So this is linear. So here unit, you specify here how many units should be in your output, that is number of neurons in your output, as you have in this case. So you have just one neuron in an output, so that's why you have one here. And here you specify in your input shape in this place. So your input shape here, that is your x here, is just a one-dimensional array. So that's why you have just one here. Then you can compile. As we go on, you learn more. You've already learned about this loss function, which is mean square error. Then the optimizer, that is the this is the technique to which we be able to measure to be able to determine the how you take your steps towards the local minimum. The loss function actually measures how far away is your prediction from the actual value, while the optimizer is trying to help you take a step towards the global minimum. So in this fitting, that's actually where you draw a line into your training set, and you continue to do that many number of times. That is your epochs, is how many times you want to go through the entire data set. In this case you have 500. Then you can return your prediction and you take the first value. So that is just a code to do that. In order to not allow this to be too long, we're going to stop here, and the next time we'll continue with a multivariate linear regression. Thank you for listening.